In our last video, we looked at how to solve quadratic equations using either factoring or the quadratic formula. Now we're going to kind of do something a little bit different that we'll need to solve more advanced quadratic equations. And we want to look at what's called complex numbers. And essentially the idea is, we worked with square roots before. If I want to know the square root of 4, we all know it's 2. The question becomes, if I have the square root of -4, what do I do? Because you all know you can't take the square root of a negative. Unfortunately, square roots of negatives occur a lot in the problems we solve, so we need a workaround here, and we use complex numbers, and essentially complex numbers have the property where the square root of -1 is equal to I. It's an imaginary number, which really just means the square root of -4 I can rewrite as the square root of 4 times the square root of -1. The square root of 4 is 2. The square root of -1 is I. And now I can kind of solve out these negative square roots. If it's a little bit confusing, for right now at least, anytime you're taking a square root, if you end up with a negative inside the square root, just make it positive and replace the negative with an I. And you'll be good for right now. The problem is, once we start having these i's floating around in our problem, we've essentially created a new type of numbers, complex numbers, and we need to make sure we understand how to work with them. So we want to run through all the operations on complex numbers, and then if we have time, I might have to make another video, go through how to actually use them in problem solving. So the way it works is, for complex numbers, there's a standard form for writing them. We say a plus or minus bi, where a and b are real numbers, and I is that imaginary I. So essentially, if I have something like 2 plus 3i, 6 minus 4i, 7 plus i, all of those are complex numbers in standard form, and that's the form you have to write them in. A real number plus or minus a real number times I. And we'll kind of go through the different things that can occur and how to algebraically manipulate complex numbers to get that standard form. So we're going to run through the operations to start with addition and subtraction of complex numbers. So suppose I have 2 plus 6i plus 3 minus 2i. If we had no idea what the I was, your brain would just naturally say, well, if I'm adding a bunch of stuff together, combine like terms. And for the purposes of this, that's all you have to do. So I get a 2 plus a 3, which is a 5. 6i minus 2i is 4i. And there I go. There's my answer. So as far as it goes, addition and subtraction, really you don't do anything different. I could just replace these i's with x's, and you would do the exact same thing. Combine like terms. If I replace this positive with a negative, you do the exact same thing, but distribute your negative in. All that really means is, for addition and subtraction, there's nothing really new or different about complex numbers. You just combine like terms. I don't want to spend a lot of time on that. So next we have multiplication. Say we have 2 plus 4i times 3 minus 5i. I want to multiply those out. Well, again, if those i's were just x's, you would immediately say, FOIL that. So just FOIL this. So let's see, 2 times 3 is 6, 2 times negative 5i is negative 10i, 4i times 3 is 12i, 4i times negative 5i is negative 20i squared. If I combine like terms, 6, negative 10i plus 12i, negative 10 plus 12 is positive 2i minus 20i squared. I combined all the like terms I could, but the problem is, we said complex numbers have a standard form that looks like that. And that's clearly not standard form. I have a real number here, I have the number with an I here, but I have an I squared there, which isn't part of standard form, and I have to get rid of it. And there's a trick for it, one other property we need. We said by definition, the square root of -1 equals I. I want to know what I squared is, so square both sides of this. Then I get I squared is equal to the square root square cancels, and I'm left with -1. Which means I squared is -1. I can substitute that in here. And I get 6 plus 2i minus 20 times -1. -20 times -1 is positive 20. So 6 plus 2i plus 20. And now I can combine the 6 and the 20. And I get 26 plus 2i. And now that's a complex number in standard form. So just kind of be aware, if you want to multiply complex numbers, just FOIL. It is no different than the foiling we've been doing, except that at the end you get this I squared term, and then you just replace I squared with -1 and simplify from there. So let's see, we've done addition and subtraction. Next up comes division. And when we write division, there's different ways to kind of write out the problem. A lot of times we write division like this. We'll say 2 plus 2i divided by 3 plus I. Which we understand the fraction means division. It's just to make things clearer for what we want to do, we generally write our division this way with complex numbers. And the problem is, what exactly do I do? I know standard form is a plus or minus bi. I have a plus or minus bi divided by a plus or minus bi. What do I do to make something like that look like something like this? And there's a trick. For right now, this trick maybe doesn't make a lot of sense, but once we use it, we'll see how it works, and then it'll make a whole lot more sense. In math, we have what's called conjugates. And essentially, to conjugate something, you flip the sign. What we're going to do is look at the denominator and find its conjugate. The conjugate of 3 plus I is 3 minus I. All you do is flip the sign. There's a reason for this, which we will see in a moment. So just kind of bear with me on this. You guys know how algebra and fractions work. If I multiply by 3 minus I on the bottom, to keep things equal, I have to multiply by 3 minus I on top. Which basically means I get to practice my foiling a little bit. So FOIL on top. 2 times 3 is 6. 2 times negative I is negative 2i. 2i times 3 is 6i. 2i times negative I is negative 2i squared. On the bottom, 3 times 3 is 9. 3 times negative I is negative 3i. I times 3 is positive 3i. I times negative I is negative I squared. On the top, we know I squared is -1, so this becomes -2 times -1, which is positive 2. 2 plus 6 is 8. 6i minus 2i is positive 4i. On the bottom, negative 3i plus 3i cancels. Negative I squared is -1. So this is -1, which is positive 1, and I get 9 plus 1, which is 10. And now we kind of see the trick here. If you multiply a complex number by its conjugate, you end up with an integer, or you end up with a number, not necessarily an integer. In this case, we got an integer, which means the i's disappear, and that's a whole lot nicer for me. And if you kind of look at it, we ended up getting 10. The two coefficients, the two real numbers here, for the a plus or minus bi, a is equal to 3, b is equal to 1. 3 squared is 9, 1 squared is 1, 9 plus 1 is 10. Which means when you're solving these out, you can do the foiling and get your answer, or you can kind of shortcut it. There's a rule that says if you multiply a complex number by its conjugate, you end up getting the sum of the squares of the two coefficients, 3 squared plus 1 squared. The actual math way of writing this, just really quickly, we say something like this. If z is equal to a plus bi, its conjugate we call z bar is a minus bi, and the rule says z times z bar, a complex number times its conjugate, is equal to a squared plus b squared, the sums of the squares of the two coefficients. So we can just use that. And the reason we care about that is because now that there's only one term on bottom, I can rewrite this as two separate fractions. 8 over 10 plus 4 over 10i. I can reduce that to 4/5 plus 2/5 I. And now I have this in standard form. A plus or minus b times I. When you are solving these problems, your answers always have to be in standard form. Which means if you write your answer like this or like that, it's going to be wrong. You have to write things in this form. A plus or minus b times I. The last little thing that we want to look at with complex numbers, and I in particular, is a trick called the periodicity of I. And we're going to do this really quickly. The idea is, I know I to the 1 is equal to I squared is equal to -1. I cubed, if I want to solve that out, is I squared times I, which is -1 times I, which is -I. I to the 4th is I squared times I squared, which is -1 times -1, which is +1. Don't worry, we're going somewhere with this. I to the 5th is I to the 4th times I. Since I to the 4th is 1, it's 1 times I. I to the 6th is I to the 4th I squared. I to the 4th is 1, so it's I squared, which is -1. And now if we look, we get I, -1, -I, 1. I, -1. And by a quick little bit of guessing, we can tell I to the 7th will be -I. I to the 8th will be +1. And then this pattern will keep on repeating. Again, it's what's called the periodicity of I. The powers of I repeat every 4. I has period 4. But what that means is, if we want to find I of 42, well, all we really have to do is find the highest multiple of 4 that is less than or equal to 42. So in this case, that's I to the 40, I squared. I to the 40 is I to the 4th to the 10th, I squared. But I to the 4th is just 1, so that's 1 times I squared, which is I squared. And I get -1. So really, quickly, just to kind of end this and have fun, I to the 413. Well, what's the highest multiple of 4 less than or equal to 413? I think it's 412. So that's I to the 412i. But any multiple of 4 just gives me 1. So that goes away. And I get I. All things being equal, the usefulness of this for the math we're doing is not all that much. It's more or less just a fun little thing we can do in math using this periodicity of I. So there you go. Have fun with it.